Alright, we're going to go ahead and get started with this chapter. You should have a set of notes that goes with this. This chapter is going to be over ionic bonding. So we are moving on. We do kind of have to keep in mind what was going on with chapter 5 and those electron configurations and what's going on with where the electrons are, and then chapter 6 dealing with where the elements are located when we start talking about ionic bonding. So we're going to go ahead and get electrons are going to be the particles in an atom that play the greatest role when we start getting into bonding between elements. So the next couple chapters are going to be over this bonding stuff. So you need to understand that the most important particle when we're dealing with bonding is what's going on with their electrons. That's how they interact with each other. Specifically, it's going to be the valence electrons that play the greatest role when these elements will bond together. Always remember atoms are losing or gaining electrons. So losing means they become positive. We kind of went through that with the periodic table. Gaining means they're going to become negative, meaning they're going to have more electrons than they do protons. A stable atom is one where the s and the p orbitals, so you should know what's going on with those s and p orbitals. So if you have an s orbital, it has 2 electrons in it. If you have a p orbital, it has 6. For a total of 8. Remember, we kept saying the magic number 8, the magic number 8. We're looking for an octet rule here. These atoms are wanting to lose or gain electrons, so their highest, and you might want to write that, their highest s and p orbitals are filled. And that's kind of what they do to form a bond. So, cations versus anions. Some atoms are going to lose. We've talked about this. These are actually are metals to achieve the octet rule, and some gain. The ones that gain, again, are nonmetals. So that kind of tells you when we're talking about ionic bonding, we're talking about a metal and a nonmetal. So metals are going to lose and nonmetals are going to gain. So metals will lose electrons and they become positive because they have more protons. And then nonmetals will gain and become anions because they now have more electrons. And you got to remember what charge those two things carry. Protons are positive, electrons are negative. So they do this again because they're trying to achieve a noble gas configuration. It's called a pseudo noble gas. So if I look at like oxygen, it starts out with 8 electrons. But it's in the column where it's a nonmetal and it's going to gain electrons. It's going to gain 2 electrons. So it's now going to have 10 electrons. The element that has 10 electrons is neon. Now, this element is not actually neon. It just has the noble gas, or the configuration, the electron configuration of a noble gas. So we call it a pseudo noble gas. And then remember what's going on with like metals versus nonmetals, knowing what's going on with their electron configuration. So I'm going to go ahead and erase this oxygen stuff. Hopefully you have that down. And what I'm going to do is work out 2 different electron configurations so you can kind of see the difference between what's going on with a metal versus a nonmetal. If I look at calcium, I'm going to abbreviate its electron configuration. It would be neon, 3s2, 3p6, oh I guess I could have abbreviated that, argon, that's okay, 4s2. So what this element is going to do, calcium, if you look at your colored periodic table, it's going to lose 2 electrons. So understanding where it's going to lose those 2 electrons, right there, it's going to lose those 2 and it's going to have a 2+ charge. On the other hand, if you look at a nonmetal, like chlorine, if I abbreviate its electron configuration, I've got neon, and then 3s2, 3p5 is its electron configuration. Well, it's a nonmetal, it's a halogen, it's in group 17, so it just needs to gain 1 electron. So it's going to gain that electron right here in this orbital, and that orbital is going to become 3p5, or 3p, oops, messed up. 3p6 instead. So now it's gained an electron, so this ion will be carrying a 1- charge. So understanding what's going on with those electron configurations and the atoms and their energy levels is important to understand what's going on when we start talking about the bonds between these elements. So when a metal loses an electron, it is gained by a nonmetal, and that's how they're going to form what we call an ionic bond. An ionic bond has to involve a metal and a nonmetal. That's the definition of it. So you've got to understand where the location, and this goes back to chapter 6. Metals are on the left side of your periodic table. Nonmetals are on the right. Metalloids are your semimetals. Those are the ones that separate it. That's kind of like your stair step that separates those two groups. So this type of bond is going to involve, keyword here, transfer of electrons, meaning one element is giving up to another. So this type of bond is very strong. And what you had whenever you were in physical science should have had a demonstration between sugar versus salt. So salt, its chemical formula is NaCl. Sugar is C12H22O11. So your teacher probably had a race to see which one melted first. So you should have timed it, and sugar definitely melted first. And the reasoning behind that is those are all nonmetals. That's a different type of bond. It's called covalent. But salt involves a metal and a nonmetal. It's a much stronger bond. Sodium actually gives its electrons up to chlorine, and they form a very strong bond. So when I tried to heat that one up for my group, it wouldn't heat up, or it wouldn't melt. So that's just kind of the comparison between an ionic and a covalent bond. So we're going to do a little review here. This is just looking at a Lewis dot diagram and a Lewis dot reaction. A Lewis dot diagram is just placing the electrons around the atom. So if I look at carbon, and I look at where it's at on the periodic table and figure out how many valence electrons, not total electrons at this point, we're just looking at valence. It's in group 14. That tells me it has 4 valence. So a Lewis dot diagram just shows those 4 electrons around that atom. I don't care where you put them, you just have to show there can't be more than 8 on one side. So if I were to do neon, I'm going to do this up in the corner. Neon has the maximum number of valence. It has 8. So you would show that as 1, 2, 3, 4, 5, 6, 7, and 8. You can't have more than 2 electrons in each side of the atom, and that's really the only stipulation to that. So a Lewis dot diagram, we're going to do a couple more down below. If I look at magnesium on the periodic table, it's in group 2. That tells me it has 2 valence. So I would draw 2 dots to say I have 2 valence electrons for that. Sulfur is in group 16. That tells me that it has 6 valence. You should have this stuff written at the top of your periodic table. My stylus does not really want to draw dots. So there's sulfur's Lewis dot diagram. And then I can look at bromine. It's in group 17. It has 7 valence. That's supposed to be 1 there. Kind of messing up there. So there's my 7 valence for bromine. So that's how you do a Lewis dot diagram. So next we're going to kind of move on and we're going to show a Lewis dot reaction, meaning what happens when these elements interact with each other and where are their electrons going. So a Lewis dot reaction, you'll need to be able to take those diagrams that we just did and show a Lewis dot reaction showing the transfer of electrons between the metal and the nonmetal. To do this, you kind of need to have a basic understanding of how chemical formulas go together. So you did learn this in physical science, but I'm assuming that you're probably going to say, I don't remember doing this, but you did. Review. So a chemical formula. What you learn to do is you learn to crisscross. This is the easiest way to figure out what's going on and how many atoms are involved. So this is done to make sure that the compound is neutral, because the charge on a compound always has to be neutral or no charge. So a compound always balances to 0. So the way that you write these formulas, I would say, okay, sodium, when it becomes an ion, it's in group 1, it's going to carry a 1+ charge. Nitrogen, is in group 15. It has 5 valence, so we learned last chapter that it's going to gain 3 electrons and it's going to have a 3 minus charge. So a lot of times in physical science what people would tell me, well, if sodium's reacting with nitrogen, they're going to give me a formula and they're going to say it's NaN. Not everything is 1-to-1. It would be perfect if everything worked out as 1-to-1, but it does not. So what you have to do to figure out how many atoms are involved when these react together, you learn to crisscross charges. What that means is, if I'm trying to figure out how many sodium there are, I use that number right there, the 3. So that means in this formula there are 3 sodium atoms, and then for the other one, I use that. I crisscross the charges and bring down that number. Now, when you have 1 atom, you don't write the 1 in the formula. Because nitrogen is written there, it is assumed that there is 1 atom. You don't bring down the positives, the negatives, you just bring down the superscripts and make them subscripts, and that's your formula that you're going to use to draw your picture. So let's go ahead and try to draw the picture. I'm going to erase this stuff up here because I'm running out of room, so I'm going to draw my picture up here and show the Lewis dot reaction between sodium and nitrogen. So I've determined that there are 3 atoms of this and 1 atom of that. So that tells me in my picture I'm going to have 3 sodium atoms. And I'm going to kind of cram this in here. So each one of those sodium atoms, if I look at the periodic table, have 1 valence electron. So 1 dot. In my picture, I also have 1 nitrogen atom. And that nitrogen atom starts out with 5 valence electrons. So that tells me that nitrogen needs to gain 3 electrons. Well, we have 3 sodium atoms over here that need to lose their electrons. So that electron's going to go there, that electron's going to go there, and that one's going to go there. Nitrogen is now going to have 8 electrons around it, so it's got its octet. Sodium needs to lose its 1 valence electron, and it's happy. So that is a Lewis dot reaction for sodium nitride. The important thing here is this right here, getting the formula, because if you don't have the formula right, then you won't be able to get your picture right. So we're going to look at calcium and chlorine. So calcium is in group 2. It loses 2 valence electrons to have a 2+ charge. The metal is always going to be positive. The nonmetal is always going to be negative. Chlorine is in group 17, nonmetal. It gains an electron to have a 1- charge. So if I crisscross these charges, my formula is going to be Ca is 1, Cl is 2. So that tells me when I draw my picture, I'm going to have 1 calcium and 2 chlorine. So when I draw this, I'm going to have a calcium, a chlorine, and a chlorine. And then I go back for my picture and I look at how many valence electrons these have. Calcium is in group 2. It has 2 valence. The chlorine atoms are in group 17, so that means they each have 7 valence. I'm really not good with the stylus and trying to draw these. Okay, so each one of them, oh, I got too many on that chlorine. Okay, you guys are probably already done with this, but each chlorine has 7 right now. Not very good 7 dots, but good enough. So now I've got to show how calcium is giving up its electrons to those chlorine atoms. Each one of the chlorine atoms need to gain 1 electron. The calcium has 2 to give up. So this one is going to go here, so you're going to show me with an arrow where these electrons are going. So that is a Lewis dot reaction for calcium chloride. So let's try 2 more examples. If you want to try to pause me and see if you can do this on your own, I will work them out and you can kind of check your work. But eventually you are going to take a quiz over these and show me that you can do these Lewis dot reactions. So aluminum is 3+, and you should have a periodic table that has all of these on there for you, so you should be able to look them up. Sulfur is 2. So this formula would be Al has 2 atoms. S has 3 atoms. So then my picture is going to have 2 aluminum and then 3 sulfur. So now I'm going to attempt to put my valence electrons. Aluminum each has 3. And then each sulfur, if you look where it's at on the periodic table, they each have 6. Okay, so there's really bad 6. Anyway, sulfur each has to gain 2. So 2 of these are going to go 1 there, 1 there. Now that sulfur has 8. 1 there, 1 there. Now that sulfur has 8. And then 1 there, and 1 there. And that sulfur now has 8. So that's how they interact and form an ionic bond. The last example, I have potassium, which is in group 1, so 1 plus charge. Oxygen is in group 16. It carries a 2 minus charge. So the formula for these would be K has 2 atoms. O has 1, so it's K2O. And my picture means I'm going to have 2 atoms of potassium and only 1 of oxygen, so that means I'm going to have 2 of these and 1 of these. My potassiums again are in group 1, so that means each one of them has 1 valence. My oxygen is in group 16. It's going to start out with 6 valence. So there's my 6 valence, and then I show how there is a transfer of electrons from the metal to the nonmetal so that oxygen can have an octet and potassium is giving up its valence electrons. So that is how you do a Lewis dot reaction. Go ahead and answer your WISC form, and you are done with this assignment, and you will probably have a quiz over this when you come in next time. Thank you.